I want to welcome you to Pre-AP Chemistry at Allen High School. My name is Dina Leggett. I am the advanced chemistry teacher. I teach Pre-AP Chemistry and AP Chemistry at Allen High School. Yay, Eagles. Now, in this unit, what we're going to be doing is studying thermochemistry. That's heat and chemistry relations, but we're going to do it with a flipped approach. And I want to say a special thanks to Jonathan Bergman and Aaron Sims for coming up with this idea, not only coming up with it, but widely disseminating this information through discussion forums and on their website, Learning for Mastery. So with that in mind, let's go on and talk about energy. Now, energy is, broadly speaking, the ability to perform work. There are many forms of energy. We have mechanical, heat, bond energy, and chemicals. There'd be a lovely chemical energy transformation I'd like to get involved in today. We have light energy, electrical energy. Now, there's all these different types of energy, but we need to bear in mind a key law of science. And that is the first law of thermodynamics, which says that energy cannot be either created or destroyed. Now, when you take AP Chemistry with me, we'll talk about the second and third laws of thermodynamics. But for now, you need to know that the first law says we cannot create or destroy energy. However, it can be transformed. And that's what allows some of the wonderful things that we have in life to happen, is this transformation of energy from one type to another. For example, the batteries in your car are going to convert chemical energy to electrical energy and help your car run. Now, there are two broad categories of energy, and you should be familiar with these two broad categories. The first is kinetic energy. I hope you had this back in middle school. We have kinetic energy, energy of motion, and potential energy. Honestly, potential energy can be a little tough to understand in the context of chemistry, but we're going to try to get a good introduction anyway. Now, let's start with kinetic energy. I think that's the easiest to understand. Kinetic energy, remember, is energy of motion. Now, the calculation for kinetic energy is 1/2 mass times velocity squared. So M stands for mass, V stands for velocity. Now, the mass has to be in kilograms. The velocity has to be in meters per second. Those are our SI units. And when those units are used properly, we get this derived unit, kilogram meter squared per second squared, also known as a joule. We'll be using that unit quite extensively in this unit, the units of joules and kilojoules, which are 1,000 joules. Now, if you notice, mathematically, this must always be positive. And remember from the gas unit, that's why we use the Kelvin scale for temperature, because temperature is a measure of the average kinetic energy, and if kinetic energy has to be positive, it's only logical that we have a positive scale for our temperature as well. Now, I wish we had time to do some math with this. You will likely do more mathematics with this in your physics class next year, but time doesn't permit us to delve into that right now. So we're just going to go on to the conceptual aspects of this. Now, again, remember what I said is that temperature, and we'll talk about the units we have to use in just a little while. Temperature is the measure of not exact, but average kinetic energy. So what we find is that the higher the temperature, we have, the faster the movement of the molecules. So high temperature reflects faster movement. Now, if all molecules, if a system is at the same kinetic temperature, we say they have the same average kinetic energy. Now this graph down here shows that on the y-axis we're just looking at number of molecules, and this is velocity, which is related to temperature. Okay, so this would be one temperature, and you see it maxes and then tails off. This is called a Boltzmann distribution. And if I increase the temperature, you notice that it shifts over to the right. More molecules are moving with a higher velocity. So this would be the higher temperature, and this one would be my lower temperature. Now another picture that I think shows this very well is this one here. As heat is added, so this is before, and you can hardly see there's little tails here on these atoms moving along, and those tails are supposed to represent the speed at which they're whipping around in that container. Now as I add heat energy, when we talk about heat is the transfer of energy, so as I transfer energy, that transfer is going to be measured as an increase in temperature. And that's because you notice, and the tails are trying to depict that the molecules are moving a little faster at the higher temperature. And so you add heat, molecules move faster, they have a higher kinetic energy, and we measure that as an increase in temperature. Now, in the next little video, we're going to be looking at definitions of heat in a little bit